to be forced into a more open conformation, which I will talk about more. So the structure of shikimate kinase, there's like two domains. The first is the lid domain, which covers over the shikimate acid to form a tightly closed enzyme, and the lid domain is right here. I think it's mostly this like loop thing that like closes over shikimate acid right here to like close it over. And then there's the SB domain, which is where shikimate acid binds, and then that also moves right here. And so basically what they're trying to do is to find an inhibitor that makes the enzyme stay in the open conformation so that catalysis cannot occur because it has to be tightly closed for catalysis to happen. And so they base their inhibitors based off of this enzyme, which is an E114A HPSK variant enzyme with this nithapiline derivative bound. And so you can see here in gray, this is with shikimate acid bound, and then with green is with compound 7 bound to it. And you can see that the compound 7 like makes it and forces it into a more open conformation of the enzyme, making it like basically catalysis can't happen. And the way that it does this is it actually displaces an essential arginine. And so then it changes the lid domain specifically so that the enzyme can't close and catalysis cannot happen. And so based off of this information, they
Can I interrupt for 1 second, Lindsay?
Yeah.
I just want to point out how unusual compound 7 is. I don't know if any of you might remember in some E2 experiment where you made those azo dyes. Do you remember that? Anybody? I think you did an experiment like that. Does anybody have any idea what I'm talking about?
I don't think we did that one.
Okay, maybe you didn't.
Isn't that with the brown dyes, the brown colors, or no?
I don't remember what color they were. They might have. I think they were like orange, actually.
Oh, okay.
But this thing is weird looking. Like I don't like this is. I don't know where this came from. Because that is not like an inhibitor looking molecule. That looks more like a pH sensitive dye, like a pH indicator or something like that. So I guess why I'm saying this and why I'm interrupting you, Lindsay, I'm sorry, I apologize, is that this is probably had some fortuitous backstory to it. In other words, yeah, anyway, it's because it doesn't look anything like shikimate, which is what all their previous compounds were like, right? Mm-hmm. So anyway, I just thought that was interesting.
Also, I'm so sorry, all of the figures are blurry and I don't know why. And so they made, they came up with these potential inhibitors, and what they wanted to kind of copy from this is the aromatic compound, and they thought that like the larger substrate would create a greater change in like causing it to stay open. And so they kind of came up with like 3 kind of groups. So the third group all have like this O-benzyl group, which is an oxygen bounded to a CH2 bounded to either any of these aromatic compounds, and they did all of them. And then compounds 4 and 5 have like this azide kind of action going on in the instead of the O-benzyl group in the aromatic group. And then the compound 6 is the same as all of compounds 3, except that they added a amide group onto the C3 to see how that would affect the movement of the enzyme. And so now I'm just going to talk about the synthesis of them. And so the synthesis of compound 3, which was the O-benzyl groups, started with just putting the aromatic groups on. So they snapped on the aromatic group with the CH2, and then the second group was just the second reaction was just acetyl hydrolysis. And then they use something called amberlite IR120 ion exchange resin. And so basically what it is it's this bead, and it has all of these like little groups coming off of it. And they use it to, it like works in place of an acid to protonate specific places that they want to protonate. And something interesting about it is that it's just super easy to use. So it's just these beads, and you like throw them into like the reaction flask, and you let it react. And then you filter it, and then you rotovap it, and then there's like no traces left of it. And that's like why I think they used it, was because it was super easy to use and also didn't leave behind a lot of excess like waste or like it didn't, I can't think of the word, but it didn't, yeah. Do you know what I mean?
Yeah, these are wonderful. Yeah, they're easy to use, and then you can even reuse them. You can just wash them and use them again if you wanted to. Yeah.
Yeah, okay. And so then for the synthesis of compounds 4 to 5, the first reaction is one of those that has like 2 reactions in the first, and it's labeled as 1 reaction. And the first thing they do is they mesylate this, the alcohol group, and then they just do an acetal deprotectant with acid. And then B is the epoxide formation, and they use similar reagents to what Beth and Naya talked about, I think, with the epoxide formation. I think that's who it was in the past, like Wednesday type thing.
And I think this synergy is amazing, actually.
Yeah.
Yeah.
There's like this, all of the synthesis like use something like related to one of the things that we talked about on Monday. And then C was an epoxide opening, and I think they used an azide to open the epoxide. And then D is actually click chemistry, which we talked about earlier as well. And basically what they do is they click on the alkane onto this azide group right here, and it has like the aromatic attached to it as well. But what's kind of weird about it is that like with click chemistry, you usually do it to like do a bunch of reactions at once, but they only made like 2 of them with the click chemistry. And then a basic hydrolysis, and they also sometimes use the amberlite resin as well. So the next synthesis is actually very interesting. They use the Mitsunobu reaction. And so basically what the Mitsunobu reaction is it's a shortcut to using the alcohol group as a leaving group. And so what they do is like you usually have to like do the mesylate and then use the mesylate as the leaving group. But what actually happens is they just kind of shortcut it right from using OH as a leaving group and then attaching on that nucleophile. And like they usually use dead, but they actually use diad. And what usually happens is the PPH3 will attack the nitrogen, and then the double bond will go to the nitrogen to form an anion, and then you're left with this right here, and then then a carboxylic acid will come in, and then they'll take the hydrogen from the carboxylic acid, and then
so in that case, Lindsey, this is just an example of where the carboxylic acid is the nucleophile, but it doesn't have to be a carboxylic acid.
Yeah. So it's the nucleophile is a carboxylic acid, and then so then it deprotonates the carboxylic acid, and then you have, this is just like waste. The PPH3 pops off, I think, and then this is not what I remember it being.
So it becomes attached to the alcohol that's undergoing.
Yeah, it becomes attached to the alcohol.
Yeah.
And then you're left with this molecule right here, which is what you wanted with instead of the hydrogen, you have the substituent attached, and then you're left with PPH3 bunch PO. Yeah, and then it's just a basic
So
hydraulic.
can I just say one thing real quick?
Yeah.
Actually, because your scheme on the right too, with sort of the generic form of the nucleophile, is a really good one. That the I would just say that the Mitsunobu. I was very happy when Lindsey wanted to talk about the Mitsunobu reaction, because I think that for people like you, this is definitely a reaction that you should know. That what it does is it takes an alcohol, an sp3 hybridized alcohol, and it replaces it with a nucleophile. I think it's important, although maybe not strictly required, that the nucleophile itself has a hydrogen. So it can be a carboxylic acid or a thiol. It can even be an alcohol on its own, or there's a variety of things that you can use as the nucleophile. And then what happens is you activate the alcohol for substitution by that combination of the diethyl azo dicarboxylate and triphenylphosphine. And then the substitution happens in like one step. It's a very popular reaction to do nucleophilic displacement of alcohols, instead of, just like Lindsey said, like you've seen a lot by now, where you can make the mesylate and then displace it. Here you can displace it in one go, and you can also even have pretty weak nucleophiles. Like in the left, they use a carboxylic acid, which is like kind of a crappy nucleophile, but in a Mitsunobu context, it works really, really well. So it's just a good tool to have in your mental toolbox for making things. We actually use it a lot at, if you remember, like the JKR compound is an adenosine, where at one position we substitute one of the alcohols on ribose with like a sulfur linker, and we use the Mitsunobu to make that bond. So we do it too. Okay, I'm sorry, Lindsey.
No, you're good.
Okay.
And then it's just a basic hydrolysis followed by that with NaOH, THF, and RT. And so what they found was that, so they tested the inhibitors on the enzymes, HPSK and MTSK. HPSK is Heliobacter pylori, which causes stomach ulcers, and MTSK is the bacteria that causes tuberculosis. And what they found was that like compounds 3 and 6, H and I, worked really well, but compounds 4 and 5 didn't really work that well at all. And so what this is showing is it's showing the micromolar Ki amounts needed for the inhibitors, like the least amount needed for the inhibitors to work against the enzyme. So you want like the smallest number possible. And you can see that like even with the MTSK, all of the numbers are like pretty large. But with the HPSK, you can see that like they are smaller, like specifically like 3I is like super, super small. And they're all just like, and so is like 3E. And they said that those were like the 2 most potent inhibitors. And so they kind of thought that like the reason why it worked better for HPSK instead of MTSK was because of the variance within the shikimate kinase enzyme, was that the HPSK had a smaller active site than the MTSK active site. And they thought that like, so like these structures aren't actually what they like crystallize. They are like calculated enzymes, but they thought that just because it's a little bit smaller, even though the aromatic molecules are like larger, they will just work better. Sorry, I don't know what happened. So it has a smaller active site, so the aromatic molecules and the larger substituents on the ends of them make a larger change in the, like causing it to be more open in the active site than like when it binds to it, it makes the opening be more open than if the than in the MTSK. So yeah, that's it.
So like not great compound. Oh yeah, good. So like not great compounds, right? I mean,
No.
yeah.
They're really not. Like 2,000, like that's huge.
Yeah. You know what? I mean, if it was me and I started making like the 9th and the 10th and the 11th compound and just not seeing like a ton of improvement, I probably would just change the group, right? I mean, start putting different things on there because you know what I mean? Like these are all pretty similar. Some of them just have a methyl group in a different position. You know what I mean? Like they're like trying to fine tune, but they're not that, it doesn't seem like they're at that phase yet. They probably should have explored more chemical space, if you know what I'm saying.
Yeah.
But based on the results, this would be a good chemistry question for all of you. And you're looking at these aromatic substituents, particularly the set that are labeled 3A through I. What seemed to be helpful? What's the best compound?
3E.
How would you characterize 3E?
Can I give it a shot?
Sure.
Does it have to do with like a withdrawing group?
It does.
Is
I mean,
like a withdrawing substituent, I mean?
Yeah, so nitro groups are the most electron withdrawing groups of like the normal set. And disappointingly, I think it's the only one, right? In other words, so they do have one with a fluorine, but fluorine is not nearly as electron withdrawing as nitro. And that can make a big difference. So, I mean, I'm a little surprised that they didn't make a set of even just like the paranitro compound, right? Or whatever, just to see, you know, or you could have other electron withdrawing groups there to see if that makes a big difference. And also, like you guys probably don't know this, but like pyridine, for example. Do you know what pyridine is? Right, it's an aromatic ring like benzene, but it has a nitrogen substitution in it. Pyridine is an electron poor aromatic ring. So they could have tried a pyridine and they didn't. You know what I mean? Like they probably should have done that stuff instead of just making a bunch of rings which are basically otherwise similar, I would say. But
Lindsay, I have a question.
Yeah.
So how are they getting like two, like in the lanes that are like the MTSK and HPSK? How are they getting two different numbers? Are they using like a formula? Like I just like don't know what that means. I guess.
Two different bacteria that they tested it in.
Oh, okay.
So the MTSK is the enzyme, the shikimate kinase for tuberculosis, and then the HPSK is the shikimate kinase enzyme taken from Heliobacter pylori, which is what causes stomach ulcers. So they just tested it in two different.
So I mean like, so how it says like 360 plus minus 14, like where are those two numbers coming from?
I think it's based on the inhibitory potency, and I think they find it like just based on. So do you remember how I talked about like the PK LDH assay?
Mm-hmm.
So they put the compound, the enzyme, and the PK LDH assays. I'm guessing that's how they measured it, and then they find the potent, like the change in the products based on how the color changes. So like I'm pretty sure like it's just like measuring the amount of products, and they want the amount of products to go like be smaller.
Is it like a standard error?
What?
Plus or minus, is that like a standard error? Like
Yeah.
for a confidence interval? Oh, okay.
Yeah, so they would have repeated these. I don't know how if they might have said like in their in the experimental section of the paper. But typically people would like repeat the experiment several times, like 3, 4, 5 times. And then you would get a range of numbers. And then I don't really know a lot about statistics, but there are certainly programs that can calculate it for you. That it basically is like the real number and then the uncertainty in that number, which is the plus or minus, right? So that would be like you can it could either be standard error or there's other types of ways you can designate what, like it could be like a 95% confidence interval or things like that. So just because you've repeated the experiment, this error doesn't look bad on these actually, which is probably because their assay is pretty good and stuff. Yeah. Yeah, so I used to say these are the shikimate kinases sort of like what I like about this paper is that they just sort of built off of the substrate, right? Because their starting material was actually shikimate acid. And then they did some pretty straightforward chemistry to derivatize one position with sort of with like a model. They had an idea of like that it would work, and it kind of worked. Like they got some compounds where that aromatic ring seemed to be helpful, right? So it's pretty good. But this is like the difference between like early phase, like what can we get to bind to the enzyme and affect its activity like at all, versus like a much more advanced, like where people really, really understand a lot about it, right? Like in Beth's paper, like she showed like, and in that paper, there's like dozens of crystal structures, right? And here they have to model, so that's another big difference, right? Like a model is a computational guess about how the molecule might be binding, whereas a structure is real, and then you can make decisions about what molecule to make based on what the binding pose is in that like real data. So unfortunately, these people don't have that. So nice. Thanks, Lindsay.